as an investigative laboratory, most of our projects start with definition of a problem, which means that this laboratory has to have a variety of investigative approaches so that once you get the first piece of evidence, you can move on to another piece of evidence and be able to either accept that as a cause of the problem or not. This, in fact, is what we mean by industrial forensics. About 2012, we were approached by Oak Ridge National Laboratory to consider a problem of monitoring the impurities or materials that were in the recirculating water cooling system for the SNS. There was a desire not only to monitor those impurities, but also to use the information that was gained from that monitoring to predict things that were happening in the system, perhaps a little bit like preventive maintenance, using a combination of scanning electron microscopy and X-ray diffraction. You can see not only the particles on a particle-by-particle basis, but also to look at their morphology, size, and their chemical composition, allowing us also to make predictions about where the particle originated. So that over time now we've developed a pattern which allows us to tell when something unusual is going on. This transmission electron microscope is capable of magnifications up to 1,000,000x. Because of the electron power here, we're able to look at internal structure of carbon fibers to detect not only surface imperfection, but also internal imperfections in carbon fiber, which will give manufacturers a key to the quality of the material, but also where that quality breakdown originates. Another concern about carbon fiber is starting with a precursor material, the objective is to burn away everything except the carbon skeleton. And one of the concerns that a manufacturer will have is for a particular precursor, are there materials emitted during that process that are hazardous to employees working around the area or harmful to the machinery being used? So this instrument, this TGA mass spec, allows us to take some material and heat it up to temperatures up to around 1,000 degrees centigrade. The effluent is piped into a mass spectrometer that allows us to tell what's present, or by gas chromatography what's being cooked off. A bench scale treatability study is just our way to talk about any chemical process that can be modeled at the bench and then tested. So if you wanted to look at the potential for an accident, for example, or if you wanted to investigate an accident that had happened, or if you wanted to try to model a process that was going to cost several $100,000 or millions of dollars to implement, you'd try it first at a smaller scale to see if it works. This investigative approach is applied in many areas to things like the resins that are used to clean up effluents from nuclear power plants. All of them are still here. So this is a potential solution. We're told, here's the problem to solve. It's up to us as chemists, microscopists, physicists to recommend a solution and to implement that solution and solve the problem.